this. I'd already drafted it before, but it's an announcement about next week, how next week is going to go. It's the exam fix-it week. So as far as the fix-it stuff goes, everybody will have the opportunity to resubmit one lab and one hack. I just posted this, so I have actually not reopened the hand-in, so when I get back to my office, I will open that up. But you'll have to go to your lab, go to your hack, show an LA that you fixed everything, and then they'll update your grade if you want it. Yeah?
Can you save the one lab, one hack thing?
That's a good question. We're still thinking about that. If you've done well on everything up to this point, keep it up. Don't falter. If you end up not using it in the first 5 weeks, then we can consider that later, right? But then anyway, the details are right there. I will open that up later. Here's the exam, maybe the more important thing. Well, it's only 50 points or something like that. I forget what it is for this class, but it's just a couple of exercises, maybe 2 or 3 exercises, I forget. I've only drafted it. But in any case, it will take place 1 week from today, Friday, September 23rd, right? That's 23rd, right? Yeah, 23rd. There will be no lecture that day, right? So I won't be here at 9:30 a.m. You don't have to be here either, because the instructions will open up on Canvas at 9 o'clock. You will have until that midnight to turn it in. It is not going to take you 15 hours, right? It is designed to be about an hour, hour and a half, maybe at most. Both C and Java exercises will be on that exam. It's open book, open note, open computer, because in fact it's required computer, because it's going to be very much like your hacks. You're going to be given several programs to write, clean them up, make sure that you are doing style, documentation, design, and of course, most importantly, correctness. You hand those in through the web grader, or through the web hand-in. You can grade yourself as many times as you want up until 1 minute before midnight, Friday, September 23rd, right? That is definitely a reasonable window, 15 hours, in which to do the exam, right? So you can deal with any technical issues, any personal issues. If you want to, you can take it in the afternoon. If you want to, you can start it right at 9. I don't care, right? You can take that entire 15 hours if you really want to. I don't care, right? But do not start, say, at 11:30 p.m., right? Yeah?
Do you have to do it all continuously, or if you have
No. Nope, you can go back and forth if you want. The one thing that you cannot do is you cannot consult with any other student, individual, or anybody, period, inside the class, outside the class, anywhere, right? It is to be your own work only. So if you've been teaming up for hacks, great. You can't team up for this, right? It is an exam. It is a test of, have you been picking up the material, right? I don't think that there's any problems here. You can take it on any computer that you wish. If you need to, you can go down to the lab computers. You can stay in your home and do it there, right? Just again, no consultation or sharing, certainly never sharing of code, posting of code, solicitation for answers, et cetera, et cetera. It is stupid easy to detect that. We use MOS, which is Measure of Software Similarity, Plagiarism Detection Software. It is older than the plagiarism detection software of, say, commercial products like Turnitin. If you've heard of that before, you write a 5-paragraph essay, you turn it in, and they do plagiarism detection on that to see if somebody else has written that essay before, right? This software predates that many, many years. Why? Because we're computer scientists and we know what we're doing, right? There's nothing more structured than code. And so there's nothing more easily detectable of similarities than code, right? Because if it compiles, right, then this code was copied from this code. They changed the variables, they changed the white space. They may even changed around a couple of design things, but it'll come back as 90–95% similar. Right? I hate having to deal with it. I've actually never had to really deal with it in an honors class, so please keep that streak up, right? And just understand that it's insanely easy to find that stuff. Right? All right, I don't want to be a cop. There we go. So, we were talking about any questions on that first? Yeah.
Are there ever any like false positives?
Well, I mean, we don't just run that and then say done, right? We run that, we go in and say, okay, well, I mean, there's really only 1 or 2 ways of doing this, or doing that one line, so big deal. But you know, somebody who's engaged in that kind of behavior doesn't know what they're doing anyway, and they don't know how to hide it. And if you do know how to hide it, guess what? You wrote your own program. Congratulations, right? So if you get past the plagiarism detection software, you rewrote it, right? In fact, you caused yourself more work by looking at somebody else's and then rewriting it, right? The cognitive load to read and understand somebody else's code and then change it so that it does the exact same thing but in different ways, right? Why didn't you just do that to begin with, right? It's cheating with extra steps. Good job, right? Or doing the actual assignment with extra steps, right? So yeah, is another question or not? Yeah.
We get like some sort of like how when we do stuff in LabGrader, it gives us an expected output.
Yep.
We get like an example expected output for these.
Yeah, in the handout, yeah, of course. Right. Okay. Otherwise, you can hand it in, see what the expected output is on the grader, and then go back and fix it, you hand it in. Right? So we were talking about functions, methods in Java, of course. And they're just like math methods in that they can take some inputs. They produce one output, only ever one output, otherwise you're failing the vertical line test. And the reason that we use functions is for encapsulation, code reuse, procedural abstraction, etc. Right? We went through how to do this in C by creating, and let's just remind ourselves what we did here, by creating a prototype, which is a function declaration, the name of the function, the return type, its inputs, and then ended by a semicolon. And prepended to that is doc-style commenting, or doc-style documentation. We are not expecting you to write your own functions for the hack this week that you did yesterday, started yesterday. We're not expecting you to write your own functions for the exam. If you do, great. But if you do, then make sure that they are well documented and they actually work, right? Then we put the definition down below the main in C, right? And this is terrible indentation. How can I fix that terrible indentation without having to go through and fix it all in once? Do you remember? A style, demo.c. There we go. Open it back up, and guess what? Hey, it's fixed. Right? Remember that you can do that in your IDE too, right? All right, and then we've got a main up here that's actually, you know, executing this stuff. So what I want to do now is I want to separate those things out, right? We already did that implicitly over here in Java, right? In Java, there is no prototypes. Instead, you just create the function, right? And for now, we're going to make all our functions public static so that anybody can use them, right? Let me get rid of that. I am doing something. And we put it into this class, myMath. Because in Java, everything is a class or belongs to a class. So the way we do modular programming in Java is by separating things out into packages and classes. We collect similar functionality into classes, and then we put similar classes together in packages, and then we organize packages in a hierarchical file kind of way. Because there is a UNL folder, directory on this computer. Under that, there's a subdirectory called CSE, and if I had a subdirectory under that called foo, right, then I would have directory within directory within directory. It is a tree kind of structure. It's a hierarchical structure. Right? Obviously, I'm not going to do that, though. Okay? So modularity in Java is what you've been doing this entire time, right? That similar methods are collected into classes, right? Classes are organized, collected into packages, right? Packages provide a hierarchical directory structure that allows you to organize your code. Nice, right? Pretty straightforward, pretty easy. But what about C? It's a little bit less straightforward, but so be it, right? So in C, in general, similar functions are separated into different modules, right? You've already seen this before. Let me just switch over to C here, right? Standard library stuff is in the standard library. Standard input-output stuff is in this stdio library. Standard math stuff is in the math library. So how do we do that, right? we organize user code into separate files, right? Wherein the prototypes plus documentation go into header files with a .h extension. Ooh, that sounds familiar. Right? .h. Now we know why it's stdio.h, math.h. Those are header files that contain all of the prototypes and maybe some definitions for standard math functions. Then we place the definitions, implementations, into source files with a .c extension and the same base file name. Right. So just to show you how that works, let's go over here to our demo and start doing that. Okay, I'm going to go ahead and create a new file here. I'll call it, can I call it math.h? Probably not, because there's already a math.h, that's the standard math library. So I'm going to go ahead and call it mymath.h, right? Just like I did in Java. These are stupid names, but this is just a demonstration purposes, right? There's my header file. I'm also going to create a file with the same name, mymath, same basic name, and then a .c extension. So the .h is for header. The .c is because it is a C program, okay? And then what I'm going to do is I'm going to take my prototype and my documentation, move it over to the .h file over here. Then I'm going to take the definition down below here, right, and move it over to my source file. Right. I'll take a look at demo here. A lot cleaner, right? And that was just with one function. Imagine if my program was a big, giant, complex system with hundreds and hundreds or thousands of different functions. Do you want that all in one big, giant file? No, you want to be able to modularize code, separate it out, and organize it. The problem now, of course, is what if I tried to compile demo? Remember that it's using this AGM function here. I have no idea what that is. Right? Just like if you tried to use the square root function without including the math library, it doesn't know what the square root function is. So we need to tell it what that is. How do we do that? Well, how did we do that for the standard math library? An include. So we'll include our library here. We're going to use slightly different syntax though. mymath.h. There we go. So instead of Langle Wrangle, right, left angle bracket, right angle bracket, that's what those are called, we use double quotes here. And that's just to denote that it's a user-defined library. You could get away with the Langle Wrangle, and what that basically says is, compiler, this is a standard library. Go ahead and look in the standard space. And when it goes and says, I don't see any math library, then it goes looking in the user space, usually the current directory or wherever you configure it for. And then it finds it. Oh, okay, it's here, right? So by using quotes here, we're saying it's not a standard library. Don't bother looking there and waste your time. Go over here and look in the current directory where it should be, because it's user defined. Right? And that's why we're using double quotes here. Okay? It's still going to have a problem. It's going to know now what AGM is, but it's not going to be able to compile. This error should look really familiar to you. Right? It's the same error that you get when you forget to link in the math library, -lm. Right? It's just that instead of complaining about square root or sine or something like that, it's now complaining about AGM. That's because we need to link into it. Right? But it's over here in the header file and the .c file. Okay? So how do I compile these things into a usable library like the math library is? Right? Well, a couple things here first. Take a look at this source file. Right? Do you see your header, or do you see your prototype here? Your function declaration? Nope. So how do we bring that in from the other file over here? Same way we did it in that demo.c. Include mymath.h. Right? Should we include anything else here? Looks like I'm using fabs. Right. What else should we include? the math library. Right? There we go. Now come over here back to demo, and let's be a little bit more judicious here. I am doing standard stuff, I always do. I'm doing input-output stuff because I'm doing printf. But do I have any booleans here? Nope. All right, we can get rid of that. Do I have any math here? Remember, AGM is in my math, not the math library. So do you see any math being done here? Square root sign? Nope. Get rid of it. You should generally only include things that you're actually going to use. Now, it's not going to cause an issue like that. It's not going to cause the compiler to compile a bunch of unnecessary stuff into it. It's only going to compile exactly what it needs. It's not going to make it more inefficient. It just cleans up your code. Right? It means that you are. I could include every library in the entire standard namespace, right? And just like over here in Java, if you want to import everything, right? And then you never have to do another import again. Just import everything, right? What's wrong? Why are you complaining about that? It's not okay. It's not accessible. Java.util. Okay, there. I could have one import statement. This is called a wildcard. Import everything under java.util. Right? Is that a good idea? You're polluting the namespace. You're bringing in things that you don't necessarily need, that you don't necessarily want, and if you bring in one thing that's like a list, and you want to bring in another thing that says list, now you've got a conflict and you have to resolve that. It's also really, really sloppy design because you are not being intentional about your code. Your code should be the absolute minimum that it should be. Right? Don't bring in that cruft. Right? Likewise, I'm going to remove the cruft here. Okay. All right. So now everything should be good to go. How do I compile this mymath.c and this mymath.h into something that can be used to link in and bring this demo and this mymath together to actually work together to to create an a.out file? The first step that I need to take is I need to use GCC to compile. Right? Now, if you remember way back into the first week, I briefly showed you this flag and I said, forget about it for now. And then I said, we'll think about it later. That compile flag right there says compile, but do not link and create a.out file. Instead, go ahead and compile it, mymath.c. Right? And remember, I'm going to have to link in the math. I might not have to link in the math library yet. There we go. Yep, it works. Now I'm going to come over here and refresh this. And if you remember, when we did this to the hello program in the first week, it produced a hello.o file. Does anybody remember what the O stood for? No? 4 weeks ago, right? We don't remember. We did that, right? Vaguely remember at least? Okay. All right, so what is it? It's an object file. If I attempt to open this, what's it going to be? It's just a bunch of binary, right? If I attempt to list the contents of this file by more mymath.o, right? That's not a text file. It's just binary. It's giving me strong signals here that why are you trying to read this? You can't read this. You're not a computer, right? But I can go ahead and use a hex dump, right? mymath.o, to see that there it is. It's a bunch of numbers, a bunch of binary, a bunch of zeros and ones. Okay. All right. So now I've got this object file. I've got this mymath.o file. I've got this demo.c file. I want to bring them all together to produce an actual executable file that will run. GCC, demo.c, and mymath.o. That error message that we had before will now go away, but there will still be another error message. The same error message, but it's complaining about the other standard math library now. How do I bring that in? -lm. So, -lm is exactly basically the same thing that I'm doing by putting mymath.o file on the command line to link those two things together, to bring them in and finally produce an a.out file. Refresh, and I see a.out now. Right. And now I can go ahead and run it just like before. Right. And I hope that that's still the same answer. Right. I don't remember from Wednesday. Right. So I don't fault you for not remembering the first week, because I'm not remembering last Wednesday. Right? At least I don't remember a random number from last Wednesday. Okay, so to review, right? The demonstration that I just gave you. Let's see. We need to place the implementations into a separate source file. We use hash include, and then util, or in this case it was what? mymath.h, right? In any file that we want to bring the prototypes into, right? To compile the module, right, we use gcc-c, which stands for compile, right? mymath.c, which produces an object file, mymath.o. Right? To compile the program and link into our library, you use gcc hyphen, or no hyphens here, but demo.c, mymath.o, and possibly hyphen lm in order to bring in that standard math, standard library. All right. Any questions on that? So next week we will come back to this exercise. Again, Friday is your exam, so no class there. Wednesday I will bring in as many midterms as we want, as I have from the past 5-10 years, whatever, and we'll do as many exercises as you want as a review. But on Monday we'll take a little bit of a detour and we'll come back and revisit unit testing now that we can separate stuff out, right? Generally what you want to do is you want to separate your tests over here, your actual library code over here, and then that's what you publish. And then if you ever need to use that library code, then of course you can just use that without having to get your tests and your actual library code mixed together, right? Now that we can separate this stuff out, we can easily separate this, or we can easily separate the tests out. Oh wow, we've got a lot of time here. So let's take a different detour here today and ask, how do functions actually work? Right? So let's trace our functionality here, okay? In demo.c, we start with a function, main. Main is called, just like any programming language, it's got to start somewhere, and in this case, we'll start at main. Right? Then what happens? Then we go into AGM, and that function gets called. By the way, here's a trick. In both IDEs, this is I'm on a Mac here, so if you hold down Command, then code becomes clickable, and it'll take you right to that function. Right? I've already got that opened over here, though. Right? So I don't know why it took me to a file. It should have taken me over here to the file that was already open. Right? But you can jump to that code. Control is given over to this function, and we walk through this function until we see another function, fabs. That function gets called. Right? And come on, I can't. Control, man. I was doing this the other day. All right, fine. I was able to go into this the other day. I don't know why it's not working now. Command Option, no, it can't figure it out. Oh well. Maybe if I put something over here, square root of A. If I did it here, yeah, you can do that there. Why can't you do it in the other file, right? Oh, nope, it just took me right back here. It's getting confused, right? It's not that smart. Anyway, you can do the same thing over here, right? If you separate this out into demo, like we did before, you can go ahead and, again, same command, hold down the command, and it becomes clickable, and you can jump there. Another thing that you can do in Eclipse is you can actually go back, right? Oh, no, all right, I lost my place. Now I want to go back. There are these arrows up here. Go back to where you came from. All right, this arrow up here. And if you have the full desktop version of VS Code, I'm sure that it's more sophisticated than this browser-based version. So I'm sure that you can find the same tricks there. Okay. Anyway, we call AGM. Right? AGM calls fabs. Whatever happens in fabs happens, and it returns. Right? It comes back here with a result, And if that's greater than epsilon, then we execute this while loop one more time. We end up calling function. So the idea here is that function calls function, calls function, calls function. How does a function know where to go back to where it came from, right? How does a function have these arrows here, right? How does it know that to come back to exactly this spot when it returns from AGM, right? And that gets into a little bit of how functions work. To show that to you, where is my, then I will grab it from the other class. Nope. Functions, where's my code? I wanted it. Find some. Okay, I'm sure that I did it yesterday. Oh, it's from Spring, okay. Sorry, I'm trying to find code so I don't have to write it. There we go. So here's my program. Again, if you're not familiar with this, this is just a, oops, I don't want that, I want everything. All right, so before I, here, I'll visualize this execution because it might take up to 10 seconds here to actually compile and run. There we go, not that long. So we're gonna walk through this code. Before we do, let's understand what it does. We've got a main, and we declare two variables here, n and m, with values 10 and 16 respectively. Then we call this average function, right? Well, what does average do? It simply just sums them up and divides by 2. But instead of doing that plus, right, then it jumps to sum. So in other words, I have function calling function calling function. We're going to visualize how this is actually working, right, as we move along here. And by the way, an aside, never write code like this, right? If you wanted to compute the sum of two numbers, do you write two functions to do that? No, would you just plus and then divide by 2? This should be a one-liner, right? But I'm using this because it's a very simple example that we can understand what's going on. So take a look at that blue thing on the right, right? Before I call average here, there's a box. That box contains all of the variables that are inside main. Right? It contains argc and argv, which are its parameters. It contains n and m, which are local variables here, doubles. And it also contains average here because we're about to call the average function and then put the result into that. So this box is what's called a stack frame, okay? Every time a function calls a function, a new stack frame is created. When I go next, you'll see that a new stack frame is created. Right? And that's for average. Average has a and b, which are its parameters, and it also has a local variable called y. Those parameter variables get the variables that were variable values that were passed here on line 14, n and m, right? 10 and 16 respectively. It should be absolutely clear that n and m are not the same variables as a and b, right? They live in different boxes. They have different names, right? So those are not the same variables. Any change to b, if I changed b somehow, would that change m? Nope, because they live in different boxes. They have different names, right? So this stack frame is created. We also create another stack frame because now we're about to call the sum function, right? There's the stack frame down there, right? A, B, and X. Now again, are those A's and B's, are they the same thing as the A and B in the average box? No, right? So we've got this stack, right? Each one of these things is called a stack frame, but total, we've got a stack. When I say stack in regular Old English, what do you think of? Yeah. Oh, stack. Oh, okay. I like that analogy better because I love pancakes, but stack of pancakes. Right? What else do you stack? So the analogy that I'm going to give you is going to be dishes instead because dishes break. Pancakes fall on the floor and then you don't want to eat them. I don't know. Anyway, what happens when you, if you've got a stack of pancakes and you just made another pancake, where do you put it? Do you shove it in the middle, right? No. Where do you put it? On the top. Now the top of the stack here is actually the bottom because it's growing down, but you can imagine a stack growing up. Like just flip this monitor and turn it upside down, right? It doesn't really matter for visualization purposes that you take your computer and you flip it upside down, right? It's not actually growing up or anything like that. It's growing in memory, right? So what happens when you eat a pancake? One at a time. of course, you slice them all up and then eat them, right? But if you want to dole out one big giant stack of pancakes and you're doling them out to people, do you take one on the bottom and hand that one? Nope, you take one from the top. These operations are called pushing and popping. And the other analogy that is usually used is the dishes, right? So you've got a stack of dishes and you push a dish on the top, because in the cafeteria, they don't stack to the sky here, right? They've got this mechanism that has a spring loader and you can push it down onto the stack, right? And there's a clip there that holds the top one to it, but you can also go ahead and pop it off the top. You pop it and you go and fill your plate with pancakes, right? So that's the analogy there, that you've got this stack and you've got operations of push and pop, but you only ever work on one part, the top of the stack. Later on, when we take a look at recursion, because when function calls itself, so function calls function calls function calls function, if you have a runaway recursion and you're stacking your dishes or your pancakes all the way up, what eventually happens? Can you just keep going forever? What happens? They fall over, right? Or they overflow. You've overflowed your stack, right? Does that sound familiar? Stack Overflow, the website, that's where they got their name, right? So we've been pushing stack frames on top of the stack. The call stack here is what it's called, because we're calling functions, call stack. Now what we're going to do is we're going to return from their functions. So what's going to happen to each one of these stack frames? Goodbye. And the return value here, 13, is returned to the other stack. Right? Next. Next. We popped that stack off the top, right? And the return value here got placed into ABE. Right? Next, next. And unfortunately, it doesn't visualize it here, but when the entire program ends, that main then gets popped off and cleaned up, right? This is how functions actually work. It's like breadcrumbs, right? Let me go ahead and reverse this. There we go. How did you get to the sum function? Well, look at your breadcrumbs. You came from the average function. How did you get to the average function? You came from the main function. Right? If you go into the forest like Hansel and Gretel, you leave breadcrumbs to find your way back home. Right? This is what it is. A stack is a breadcrumb. Right? How did you get here? How do you get back? All you have to do is turn around, see the breadcrumbs, and follow them back. How do you get back from a function call? All you have to do is follow the stack frame back down, visualize when it's building up. Okay? So that begs the question of whether or not we can do something like the following. So I'm going to go ahead and get rid of these. And I'm going to create a void function here called swap, A and B. And all it's going to do is swap out two variables. Let's do this. Int A is equal to 10. Int B is equal to 20. Right? And I'm going to print them out. Printf, A is equal to %D. B is equal to %D, and the line, A and B. And then I'm going to try to swap them. I haven't written that code yet, right? A and B. And then I'm going to try to print them. There we go. So I'm printing them out. What would you expect to be printed here? 10 and 20. If we swap them and put 10 over here and 20 over here, then we might expect it to say 20 and 10. Let's try it. How do I swap two variables? So I've got these two buckets. How do I swap the contents of the buckets? I need a third bucket, first of all. Right? Take the contents of A and put it into that third bucket. Now, this bucket is free. Take the contents of B and pour it into the bucket for A. A is equal to B. And then that third bucket, I can put that back into B. Good? All right. Let's visualize this I'm asking genuinely, did I screw up? Nope. Okay, good. And in fact, before we go on, let me show you our print statement when we get into the swap, our print statement before we leave to show you that this code is in fact correct. Okay? Oops. What did I do? Not a second int there, sorry. Visualize execution. Okay. What was that? So let's walk through this. There we go. So I've got A and B, 10 and 20. Print them out. What's going to get printed? 10 and 20, just like we predicted. Now what we're going to do is we're going to jump into that function. Swap. It receives A and B, 10 and 20. We're good. And it prints them out. 10 and 20. We're still good. So what's going to happen here with temp A and B, temp B? We place A, or 10 into temp. We place 20 into B. And then we put 10 back into A. B, sorry. And then we print them out. Hey, guess what? It worked. 20 and 10, they're swapped. Except that when we get back to the main, predict here. When we get back to the main after we've done swapping on line 18, what's it going to print? 10 and 20. Why? It's going to print its own 10 and 20 here. Right? Why? Because there are two sets of variables called A and B. Right? One of them lives in this stack frame, and the other two live in this stack frame. They have no connection to each other. Right? In fact, it would be very bad if you could, it would be very bad if you could access arbitrary values in the stack. Well, we have enough time. This is the last thing I wanted to show you today, so let's try it, because I want to show you something cool. Right? But this will end up being printed 10 and 20. So how do we actually end up like solving this problem? I do really want, for some reason, want to write a swap function. That's going to require pointers in C, and it is impossible in Java. Right? This is not something that you can do in Java. So let me show you the cool thing, and for that I'm going to have to go to an actual coding environment here. There we go. Swap main GCC demo. Yep. Oops. What? Oh, what did I do? I'm glad I did this. In swap, what types are A and B? I got away with it because it's telling me if you don't have a type there, it defaults to int, right? Thank goodness that was a warning, right? Int and int. That's the proper way of doing it. So I got away with it because it defaults to ints, and I was working with ints. Right? You can't do that in Java either. Okay. Running this, of course, I get the same exact behavior. But what I want to do is I want to try to get access to A here. This is a preview of what I'm going to show you starting after the exam week. What you can do is you can pass in a pointer, int star C. Right? And when we swap, what I'm going to do is I'm going to pass in the memory address of A. And I'm going to try, no, nope. I'm not going to, how can I force a stack smashing event? This isn't going to work. Anyway, I want to show you what happens when you do pull out one of those dishes. Swap is equal to A. Let's try this. Oh, after, darn it. How do I get a stack smashing event? Yeah. All right, fine. Darn it, I'm not going to be able to do this. Oh well, I'm sorry. So what I wanted to do is show you what happens when you go and start mucking with your stack, right? Literally, if it's a stack and you're taking out a dish, you're going to cause all the dishes to fall and smash, right? And that's exactly what they call it, a stack smashing event. For example, if I were able to say, I don't know, from this stack frame here, if I could go and muck with this stack frame over here, its internal workings, right? And there are ways to do it. I just don't remember off the top of my head how you can do it. That's called a stack smashing event. You are smashing your own memory. You are destroying, taking a hammer to your own memory. And a good operating system will detect that and say, nope, you can't do that. Right? The stack smashing event was detected and it gets killed. I know how to do it now. I know. We're gonna have to do it with an array though. Int array of 100, and then array of, let's make it really big. No, negative, let's make it small, is equal to 42. Come on, let me do it. Oh, come on. Negative 50, that should be good. You're not detecting this at all. Come on, I'm trying to smash you. There we go. It didn't call it a stack smashing event, but thankfully it ended in a segmentation fault. What I was doing is I was taking a hammer to my own memory, right? So taking a hammer to your own head, right, basically. You were trying to destroy your own program by accessing stuff that doesn't belong to you. If you've seen arrays before, you'll understand what's going on here. I created an array of size 100 elements, and I'm trying to access the 50,000th and one element, which does not exist, right? I'm going way beyond this array, and by doing that, I am illegally accessing memory, even though it's memory that probably belongs to me, right? The operating system says, look, you're screwing around with your own stack there. That's still illegal. I'm not going to let you do that. Segmentation fault, kill it. Right? So we'll get into that later on. You don't want to mess around with the stack. Instead, later on, you want to mess around with the heap. Right? So colloquially, what's the difference between a stack and a heap? When you think of a stack of pancakes or a stack of dishes, I think organized, right? When you think of a heap, what immediately comes to mind? A what? Messy, exactly. Unorganized, right? It's a heap of clothes or a heap of garbage. Where do you throw your next dirty clothes? Do you organize it into that big giant pile? No, you just throw it on the top, and if it falls down, so be it. Right? That's what a heap is. Right? It's less organized code, but it's much larger, and that's where you put big data that you need. Okay? All right. Again, we will take a little bit of a digression on Monday for unit testing. Then Wednesday we'll have review. Friday, it's up to you on how to take that exam.